Thank you for confirmation that you can hear me. I'm Adrian Bruo, and as I said, I'm product engineer in the Servo and Motion group in our company. So I'm pleased today to have the opportunity to present our solutions and our knowledge in front of you. But before we go to our topic, there are a few organizational things. So firstly, if during my presentation you will want to ask me a question, then please write it down on the meeting chat. But very important is to write it down with the question mark on the sentence end, because it will help me later in easier differentiation of questions. Yes, so if this is the question or you just talk between each other on the chat, because on the previous webinars were also these kind of situations. Because the platform has built-in Q&A module, and later I will be able to show the question and answer that. Of course, all questions will be answered after my presentation. So when I finish the presentation, when I finish the Motorizer part, I will answer the question. The second one is on the upper part of the screen. You can find the bar with button, green button, yes. If you will be interested in the shown topic, the topic that I will show, and would like to learn about in greater details, you can always sync up to reach us, and we will, for example, let you size the servos in your application and answer your doubts in greater details. Of course, if you will be interested in our solution at this point, you can also use this button and we will contact you. So I think without greater details, because this is all of the organizational stuff at this moment, I will share my screen. My only request is to tell me if you can see the screen or not, because of this problem with microphone or not. Somebody's yes, great. Okay, so then let's start. The topic for today: how to easily size the servo drives. So what we will be talking about. Firstly, we'll go about what to look for when sizing a drive, and I will briefly tell you about the topics like design of servo system and most crucial elements of servo amplifier design. Later, I will tell you which type of motor choose for a given application, and here what the moment of inertia is, yes, and because it is very important parameter, and how to deal with this inertia moment in the applications. Also, I will show you the types of servo motors, differentiate by the inertia moment, and typical load mechanics. Then we will go to the servo sizing methodology. I will also tell you about the DC common bus systems in the servo drives, what are there, why it is sometimes good to use them, multi-axis amplifiers, for example, and of course, what advantages they bring to the application. And at the end, I will sum up all of this information in the easy to understand diagram, and then we'll go to the software called Motorizer. It is free software from our company that helps you, supports you in sizing the drives in very efficient way. So it will be quicker and a lot easier. Okay, so let's start. Firstly, what is a servo drive? So if I would put it in academical way, I would say it is a closed loop feedback control system in which the input signal is some data like position, velocity, acceleration. Yes, but this is not very easy to understand the definition. So in more practical way, servo drives is the system where you have the servo amplifier, a servo amplifier which control the motor by the signal. So the PLC is commanding the servo amplifier, and servo amplifier is changing, for example, the speed, the position of the servo motor. But what is important is that servo motor has to be equipped in some kind of position sensor, so encoder. And this encoder, by the feedback loop, this signal from the encoder go to the servo amplifier, and we can know the current position of the motor. So we'll always know where the motor is, at which exact position it is, and of course which speed it has. Yes. So this is the servo drive, and this is the servo system. Of course, not always it has to be electrical. It can be any, let's say, system with this kind of feedback loop and with the gain from the amplifier. So in the typical system that is shown on this slide, we have few parts. So of course we have the PLC, yes, mostly because PLC needs to command the servo amplifier, then servo amplifier, motor with encoder, and of course mechanical side, so some kind of load, yes, connected to the motor shaft by, for example, mechanics. And when you look on the PLC, it commands the motor with position, the amplifier with position, with velocity, or with torque, for example. So this is the low voltage signal. This signal later is interpreted, let's say, by the servo amplifier, and by the PWM signal, it commands the motor, for example, to change the position, to change the speed. Yes, and then we have the feedback from the encoder, for example, that we have on this we are on this exact position. So let's say that in the typical servo drives, we have we want to achieve position B. Yes. So from the PLC, for example, we are commanding the drive to go to the position B from the position A, for example. Yes. And then the servo amplifier interpret this command, and by the PWM signal commands the motor. Motor is changing its rotation. Yes, it goes to the position, and during this time, it will provide the feedback that I'm here, I'm here, I'm here, and I'm on the position later. Yes, this will go back to the amplifier and of course go back to the PLC, to the controller. So this is how the servo amplifier look inside. So we have the main circuit and the control circuit. In the control circuit, we have a few loops like position, like velocity loop, like current loop, which of course we are using to precise control the amplifier, because we have to interpret where this command and where to go. Yes, but from the sizing point of view, we'll be interested in the main circuit also, because in the main circuit, power circuit, we have the elements which are providing the energy for the servo motor, and it is very important to know what is inside, because it will help us later with, let's say, proper sizing. So on this slide, you can see on the diagram how, on the schematic diagram, how this circuit board, so this power circuit, it will work. So firstly, of course, from the left side, let's say we are providing the voltage energy on one phase from the network or three phase from the network. And firstly, we have the converter. So the AC power, three phase, for example, like on this picture, is changed for in the DC power. Yes, but as you can see, this DC power on the converter output is still not smooth. To smooth it, so it will be straight line. The voltage will be a straight line. We will need the smoothing capacitor, and this is the, let's say, second stage of the power circuit. And then we have additional part that is called the regenerative brake. What is regenerative brake and why it is important? Because as you probably know, when the motor is rotating, of course, we are supplying the voltage to the motor. But if you want to decelerate with the motor, the load, let's say, is rotating the motor shaft. Yes, because motor wants to stop, but load wants to still rotate, for example. And because of this rotation, the voltage is, let's say, being created in the motor coils, and this energy that is created by this movement needs to find some place to go. Yes, of course, it will go to the servo amplifier. But if it would just go to the servo amplifier without any equipment to do something with this voltage, to change it for some other kind of, let's say, energy, then the circuit board, the power board would be damaged. Yes, and precisely because of that, we are using regenerative brakes, so resistors, let's say, which will change the voltage, this energy into the heat. Of course, we can use other things other than in the other system other than the regenerative brake, but in the standard system, it is like that, yes. And as you can see in our amplifiers, regenerative brake is always built in, yes. So when you are, let's say, purchasing our amplifier, you have the regenerative brake, and it will be used when needed. Then, if the load is bigger, yes, so there is a lot of regenerative energy that will comes back to the drives, and sometimes it is possible that this regenerative brake inside will be not enough. You can connect the external regenerative brake, as also shown on this picture above. Yes, so regenerative option to connect. The question in your head probably is, okay, but how to know when we need the external regenerative brake? The answer is very easy, and I will show it later. We just use Motorizer software, and this software will tell you when and if in the application you will need regenerative brake, or this built-in regenerative brake will be enough. The next part is, of course, the inverter. Yes? So we change the AC voltage to the DC voltage, and then we need to change the voltage back to the AC. Yes, and because of that, we are using the inverter. And I will not go into the great details about how the inverter works, because let's say this basic knowledge and not always needs for the sizing. But we have the diodes. Yes, we will be changing the voltage to the sinus and all of the phases of the motor. So U, V, or W will be, let's say, energized by this, powered by the pairs, by the stacks of the diodes. And later, of course, motor will start rotating. Yes, because of this change. But yes, I already said that the motor will start rotating. Yes, so it will start the movement. So we could say that it is enough. Yes, why there is still a gap in this diagram that I have above this picture, because there is additional part in our servo amplifiers called dynamic brake. This is not standard in most cases. On the market. Yeah, so I would say only few companies that provide servo amplifiers has this kind of a part inside. But what is the purpose of this dynamic brake? So let's say the dynamic brake is in basic very simple. How that works? When you have the UVW phases of the motor, as I showed before, and you connect them, then something will happen. What will happen? I before told you that when the motor is rotating and decelerating, the load will want to push it, yes? And because of that, of course, motor will rotate and rotate. So if there is a power shutdown, then the load will push the motor further and further. And if you want to stop it, so we can use, for example, electromagnetic brake, yes, when we are talking about the vertical axis. And in most cases, we are doing it. But dynamic brake can also help us to decelerate it, especially if we are talking about the horizontal axis. And the easiest way to show it is on the video. So on this video, you have two axes. From the right, you have the axis without the dynamic brake, and on the left, you have the axis with dynamic brake. So they are the vertical axis. So as you can imagine, when there is power cut off, the load will fall. Yes, and it can clearly be seen on the axis without the dynamic brake, because this is the egg, below this axis was damaged. Yes, and when we are looking on the axis with dynamic brake, this axis is still moving. So it is moving, but slowly and slowly. So deceleration is much slower, and because of that, the egg is safe. Yes, so the egg is safe, and also mechanical part of your application will be safe, because when you connect these three phases, the voltage that is being generated by the load on the motor coils will come back to the motor and stops it. So in basic, it is very simple, yes? It is very simple idea, but it can greatly help you to not damage your application. Okay, but can we calculate when motor will stop? Yes, so we know that it will slow down the rotation and slow down the movement. But for us, for engineers, it will be for the designers of the machine, it will be very crucial to know when the motor will stop. Yes, because for example, we have like 1 meter of length that the motor can stop, the axis can stop, and if we were going too much, yes, too long, then we will kick, for example, with the load some parts, mechanical parts of the machine, and because of that, it will be damaged. So yes, of course, we can calculate it using this simple formula. And with that, we know that, for example, when you have the linear axis, horizontal axis with this kind of load, I will later tell about the loads in some greater details. With this kind of load, it will stop in, like, for example, 10 centimeters or less, depending on the application. So the open question is, what will happen, especially with vertical axis without the electromagnetic brake, but not only, when our drives don't have dynamic brake and there is power shutdown and we haven't think about that? Exactly this. And that's not what anyone wants, is it? So to sum up what we have learned so far, we now know how a servo drive is built, how it is designed, how a servo amplifier works, and what using a dynamic brake gives us. So with this one brick laying the foundations for the start of the sizing process behind us, let's move on the next, which is, of course, the motors. What kind of motors do we use in servo drives? Usually not like the one shown, but I will tell you later about that. Firstly, every servo manufacturer divides its servo drives into inertia classes, And for some of them, it is 2 inertia classes. For other, like us, it is 3 inertia classes. So we have motors ultra low inertia motors, and medium inertia motors. Medium, some of the manufacturers tells it's high inertia, but for us in Mitsubishi Electric, we think that servo drives is for the precise applications, very precise application. So very precise applications. So there is no high inertia. The motors cannot be very high inertia because they are not asynchronous motor. But I will tell you about this further. So on this slide, you can see, of course, these inertia classes and the motors that are in our portfolio and their capacity. So from the left, we have ultra low inertia, MT, RT motors, low inertia, KT and ST motors, but 3000 RPM rated speed. And medium inertia, also ST and KT, but 2000 RPM. It is rated speed. It is important to remember about that there are the same series, but with just different rated speed, because it will be crucial later when we will start the sizing. But of course, I will come back to that. But before that, let us consider one more question. What is moment of inertia? Because I said inertia that, inertia this, and so on and so on. But for some people, this term is certainly associated not only with work, but also with the studies, or only with studies, because not everybody is on a daily basis in work dealing with the moment of inertia. As you can imagine, or as you can remember, not only one student landed a third term in mechanics. By the way, getting through this subject was often defined by to be or not to be at the university. Yes. Also because of the moment of inertia, because of the mechanics, we had a lot of calculations and a lot of thinking about the inertia and so on. But I will try to explain the issue in simple terms with a minimum of formulas, but there will still be some of them. But don't be scared, it will be very, very basic. So recently, a person close to me started to take an interest in figure skating. This is a discipline that you can see seen frequently at the Winter Olympics, yes. And the question is, why did I find that this was a good analogy to explain the phenomena of moment of inertia? Because moment of inertia in rotational motion is nothing more than mass in linear motion. So skaters, in order to be able to perform these beautiful combinations of movements as shown here on this movie, sometimes these movements requires rotation or a lot of rotations, yes, including ones doing in place without runaway. They adjust their body position so as to simultaneously adjust their moment of inertia according to simple formula. So this is the formula for the inertia moment. As you can see, you have the mass, and this mass is multiplied by the square radius, and this radius is the radius between the mass and the axis of the rotation. Yes. I will tell also later about that, but what is important is that this allows the skaters, the ice skaters, to speed up their turns or slow them down as required, of course. And why does this happen? Because they change their moment of inertia, which affects the angular momentum. As you can see here, some of you know, I think most of you know from the principle of conservation of momentum, that if we do not apply an additional external force to the system, then the momentum has to be constant, yes? So hence, when the moment of inertia change, the speed must also change. A little physics tricks, let's say, yes? And you can see here that we have the equation. Angular momentum equals moment of inertia multiplied by the angular velocity. So if there is no external force, of course, there will be like friction of the skates, but let's forget about that. If there is no external force, to change the speed, we have to change the moment of inertia. And how to do that? As shown on this picture, the skaters just, for example, do this movement of their arms or closer to to their body. And if it is closer, the moment of inertia is smaller. As you could see, yes, the radius is smaller. And because of that, when the inertia is smaller, the angular momentum has to be the same, angular velocity will be higher. And from the other side, when the moment of inertia will be bigger because of the arms, the angular velocity will be slower. Thought it was purely about artistic value? Well, okay, maybe not, yes, because this is the physics yet, but the question is how to transfer this to the operation of motors. So on this picture, we have two motors. From the left, low inertia, and from the right, medium inertia. So the inertia is as follows, yes? So mass and square radius. And as you can see from these motors, they are very different, yes? The low inertia motors are more longer, but the radius of the shaft is smaller. The medium inertia, from the other hand, are that the radius is bigger and the motor are smaller in these dimensions, yes? So they are shorter. When we also, there is one other thing, that the radius is bigger, because the equation for torque is just the force multiplied by the radius that you apply this force, yes? So in the motors, the force will come from the electromagnetic force, yes, and this will be applied to the magnets. So in the medium inertia motors, the magnets will have bigger radius, yes, because the shaft is bigger, and because of that, the radius will be bigger, so the torque will be bigger, of course. And this is often the case that, yes, in most of the cases on the market, you will see that medium inertia motors have bigger torque and low inertia motors have smaller torque. But this is not only that, because of course their inertia is also bigger due to the fact that you can see their design is different. Yes, so the radius is bigger, so inertia has to be bigger. But let's consider the situation when we have the motors, the low inertia and medium inertia, that have the same capacity. So for example, 1 kilowatt. We have this example in our portfolio. We have more than one example. So the power, the capacity of the motor is the same. But as I said, one has the bigger torque, the second one has a smaller torque. And when you will calculate the capacity, the power, you will just need to, let's say, the simplest way is to have the torque that is multiplied by the rotational speed. This is the angular speed, but still rotational speed, angular because of the units, yes. And of course, the capacity in watts, yes. And then, okay, so let's say 1 kilowatt motors, the same capacity. What will happen? For example, KT and ST 1 kilowatts. So from the medium inertia motors, so ST motors from our portfolio, the torque is bigger, as I said. But because of the torque that is bigger, the rotational speed has to be smaller. Yes. So as I said, medium inertia motors have 2000 RPM rated speed. Because when you have bigger torque and for between these motors, the capacity is the same, yes? So bigger torque, something needs to change and change the rotational speed. From the other hand, the low inertia motors, the KT motors, have smaller torque, but bigger speed. And because of that, they are rated 3000 and can go even up to about 7000 RPMs, which is impossible for medium inertia motors. So this is one of the things that change between these motors. There are maybe not a lot more changes, but there are still different ones, and I will say it on the next slide. But this is important to know that when you are sizing the servos, you have to remember that low inertia, medium inertia, ultra low inertia, even if the capacity is the same, they are different. And in some cases of the market, you can find the medium inertia motors that will have bigger speeds like low inertia ones, but still it will be a lot different in case of torque. And of course, in case of inertia and what we can do with them. Okay, so there is one question. Yes, we know about the inertia of the motor, but how does the moment of inertia of the load this time affect the selection of the sizing of the servo drive? Because the motors are divided into inertia classes because they have different inertia ranges, yes. And the loads also has different inertia moments, yes. And because of that, the motor also. But as you can see, before on the slides, I showed you these dynamic breakers, and I told you that we can calculate when the motor will stop when the dynamic brake is applied. And here you can see JL divided by JM. JL is the inertia moment of the load, JM is the inertia moment of the motor. So this ratio is already in this equation of how to calculate the movement that the motor will do. So how quickly it will change, it will stop. So as you can imagine, the bigger the inertia of the load, the longer it will take to stop the motor. So as you can see, the inertia of the load, inertia of the motor, and to be precise, the ratio between them is very important. And this ratio is called recommended load to motor inertia ratio. This is the screen from our catalog, picture from our catalog of the KT motors. And as you can see on these red marks, there is the value of this inertia ratio for different motors. So for example, for 600 watt motor, we have 25 times or less. Yes. What does it mean? It means that when you look for the inertia moment of the motor, so it will be, maybe it will be seen. It will be here. Yes, 0.6 kilogram centimeter square. The load that is connected to the motor can have 20 times bigger inertia maximum. Of course, we are not talking about any mechanics. Let's say just to connect the load, for example, only to the rotational movement. Yes, like bigger cylinder. And of course, the bigger the ratio for the motor that is allowed, the better. Yes, because we can drive the bigger load. But why is that like that? So to be precise, what happens if we exceed this recommended value? So on the left, now I am showing the animation of the motor that was incorrectly sized. And here you can see the command from the servo amplifier. So let's say this is the comment how the torque should look. And in the red, you see how the torque actually looks like, how the torque of the load. And of course, you can see the oscillation, but in the physical organism, in the mechanical part, what will happen? As you can see, servo wants to stop in some position. So for example, we are going from A to B, and let's say it should be smooth movement and we should stop in B. But because the motor was incorrectly sized, or because the inertia of the load was too big, it will not be able to stop in this exact point. It will just go a little bit further, then a little back, and this oscillation, finally it will stop in the point that it has to stop. But this is not how motor should behave, yes, how the servo drive should behave. Because of the bigger load of too big inertia moment, we are not able to tune the servo in proper way. And in the proper way, it will look like that. So we have the smooth movement, smooth characteristic of the torque without any problem. And because of that, we have to think about this recommended inertia ratio. And we'll later show you how to easily calculate that, because of course you will not have to do it by hand. It will be sometimes too hard. We'll use the software for that. But at this point, let us summarize what we have learned. So we already know what moment of inertia is. We know the inertia classes of the motor, yes. We know how to size drives with regard to load inertia, yes, because we know about the recommended inertia ratio. I promised to tell you which motor to use for which application, yes. And at this point, when we know so much already, it's time to do so. But before that, to definitely tell which kind of motor, looking on inertia class, we need in the application, it is best to look into power rate parameter. This is the last formula, last equation. What is the power rate? This is the torque squared divided by the motor moment of inertia. But more importantly, what does it mean? Power rate describes motor ability to accelerate and decelerate. So how quickly motor will be able to react for the change of motion parameter. So as you can see, this is the unit is the kilowatts divided by the second. What is very important in that is that it is, I could say in the physical way, how much energy we can put in the unit uh, of time. Yes, in the defined unit of time. And here I will show some diagrams, some chart of how to differentiate between the inertia classes in regard with the power rate. Because have you ever wondered about this? It is the power rate is an easy way to convert, let's say, the performance of the motors you have installed or are planning to order to install in your machine. And especially for very dynamic application, it is worth checking this value. To describe its best, we need different inertia classes. Why we need different inertia classes? Let's look on this slide. So we have medium inertia, low inertia, and ultra low inertia motors. As you already probably could predict, because ultra low inertia motors has the smallest inertia, they have the highest value of power rate. But let's think about their use comparing these motors to cars. Yes, it will be very daily use. So starting from the right side, so ultra low inertia motors, they're like Formula One birds. They fit, let's say, as many as one person, the Formula One cars, and that's without a shopping bag. Okay, this is true, yes, that you cannot, let's say, drive a big load with the Formula One cars, but from the other hand, they are very dynamic. Yes. So I never been in one. Of course, I look at them at the TV, and you can see that acceleration, deceleration, this is normal for them. They are very dynamic. They will quickly react to the change, any change. Of course, they are also very, they have very high velocity, and this is like the ultra low inertia motors. So the load you can drive will be not very big, especially compared to medium inertia, but the reaction, the time, the scope, how quickly you can accelerate will be very, very high. And then the low inertia motors, yes? So like the standard car for everyone, let's say, because the standard car can accommodate husband, wife, two children, some luggage also. If the wife gets carried away with her imagination when packing for holidays, even a lot of luggage with a trailer. However, even with that, it still retains moderate dynamics, and you can, depending on the performance of your car, of course, the same with the motors, it will be the capacity, uh, even play with it on parking late in the night, especially in winter, yes. But what is important is the same as with the KT motors or with the low inertia motors, because they are most standard, yes. They are most standard, and for most part of the application, they will fit perfectly. Because let's say most part of the application are not the best, the servo applications are not the best dynamics in the world, yes. You know, don't need the acceleration like few G. You can go with the slower acceleration, but you need to drive a bigger load, yes. So your application is not always like 10 kilograms, sometimes it's 100, 200. You can still use the standard motors like low inertia ones, yes. And the question is, then what about the medium inertia? As you can see here, for us, medium inertia motors are like trucks. So I never seen a full truck trying to race at the traffic lights. Yes, it is mostly not the case. But from the other hand, I will not go with my car, even the standard, especially not Formula One, with like few tons that the truck or better or bigger loads that the truck can drive. So it will be not most dynamic in the world, but it will can drive a big load. And this is the same for the ST motors, so for the medium inertia motors. And when we are talking about the application, let's see from the ultra low inertia motors. They are used, as I said, in the high precision application where the lowest possible level of motor response is required. Yes. So, for example, digital printing, converting, finishing, and also very dynamic manipulators. Yes, these are the kinds of application where you will need the ultra low inertia motors to achieve the biggest possible performance. Then ultra low inertia for packaging, yes, for manipulators also, the bigger loads, not the highest dynamic that you can possibly imagine, yes. And of course, let's say, for example, machinery used in FMCG and etc. etc. Because there are a lot of examples you can think about yourself, yes, like labeling and so on and so on. In most cases, we are using the low inertia motors for standard application. And then the medium inertia motors, the application when you have a very big load. So high by-wire holes, for example, roll-to-roll applications, and also more standard application, but with a lot bigger load because they have bigger torque and bigger inertia of the motor shaft. Okay, here you can see of course, the medium inertia motor, but what is important here is that the standard servo motors that we use is synchronous. They are synchronous motors, yes. To be exact, synchronous motor with permanent magnets. So we have the coils on the rotor side and magnets. The coils on the stator side and magnets on the rotor parts. So as you can see on this animation that I also showed before, the stator we have the coil. The coil are powered by the servo amplifier, yes, and because of that, the magnets inside, the magnets on the shaft, on the surface of the shaft, will start the rotation, and that's how these kind of motors are working. So let's say the principle is also simple, but always when showed on very simple diagrams, every let's say principle is easy and is simple. But what kind of advantages this design brings us? Because of course there is some advantage, and because of that, every producer of the servo drives use synchronous motor. So let's look on this torque characteristics of the servo motor that you can see. The difference is that for the synchronous motor, for the typical servo motors, the torque from 0 to the rated speed is constant. So of course, in some of the motors, it can be a little higher on the 0 and a little lower on the rated speed, but more or less in most cases, it is constant. So no matter if you are going with 100 RPM, 200 RPM, 3000 RPM, so up to the rated speed, you still have possible the biggest nominal torque. Yes, of course, later when you will go past the rated speed, you will have this slope and the torque will be smaller. But in case of, for example, asynchronous motors, yes, it is very different. And this maybe can answer your questions, because I have a lot of questions like that when, for example, I'm sizing the drives for a client, and we need to, for example, go with 600 RPMs on the application. So on this motor, we have to use the gearbox only because of the speed. No, in case of servo drives, of course, the gearboxes can be used, for example, to higher the torque, yes, but we don't need to higher the speed of the motor, because this torque is constant. Yes, for the asynchronous motor, it could be the case, yeah, because their characteristic have this kind of it is designed in this kind. They are designed in this kind, and because of that, in the nominal speed, yes, rated speed, we have the biggest torque, yes, so the nominal point. This is the best point of working for this kind of motors, but not for the servo drives, not for the servo motors. So with the servo motor, you don't need to use, for example, this gearbox only because to be in this exact point on the rated speed, because it is not advantageous for you. Yes, at this point you will just use the motor without anything, and it will be okay, no matter 100 RPM or 3000 RPM. But not only that, synchronous motors, servo motors can be overloaded. And as you can see on this is also the torque characteristic, but it contains the second part of the characteristic, so overload. In this characteristic, you have this continuous running range below, yes, and on the upper part, short duration running range. So continuous running range is up to the rating of the motor, so up to the rated torque of the motor, and then everything above is overloading. So we can overload the motor. For example, the motor has 1 Newton meter rated torque, but we need to use 3 Newton meters, but for some time, yes. Then do we have to find 3 times bigger motor? No, because of the overload, yes. But the question is how long we can overloading motor, yes, because if it would be like that you can always use this overloading part, then this characteristic will be not divided, yes. So of course you have time limits, let's say, and you can check it always in the motor overload characteristic. This is something that, for example, in our company you can find in our documentation. And for example, let's check it how long we can drive with 2 times nominal torque. So we are going to 2000% up 100 seconds, so more than 1.5 minutes. Then every step, the time will be slower. And for our motors, the maximum overloading is 4.5 times of nominal torque, and it will be below 1 second. Why we are using it then, if these times are not like 10 minutes, 20 minutes? Because sometimes, or in most of the cases, the biggest torque that motor will have to, let's say, apply to the application is on the beginning. So with the acceleration to for example, to the speed that we want to achieve in the application. So we are going with the trapezoidal, for example, slope. I will show it later. So firstly, we are accelerate. We are achieving constant speed. With this constant speed, we are driving, and then decelerate. Yes, and only for like fraction of seconds, so few seconds, you have to accelerate with bigger torque. So for example, 2 times, 3 times nominal torque, and later you will go below. Yes, because for the acceleration, the torque will be the biggest. And this kind of the design of the motors, because of that, it allows you to do so. And because of that, they are so precise, they are so dynamic. Yes, but this is allowed, let's say. Okay, but well-sized motor will be hot. Yes, and it should be hot because when we are overloading the motor, let's say why we cannot overload the motor for 3 times more than about 1 second. Because after that time, a servo amplifier will go into the thermal error, so overloading error. But why? Because motor is warming up, and also the power output of the servo amplifier is warming up. Yes, and if we could go too long with this overloading, then the motor would, for example, could break. Yes, the motor, or most likely the servo amplifier would have the failure inside. But as I said, well-sized servo motor should be hot, and temperatures even up to 100, yes, 100 Celsius degrees do not mean that don't mean that it is the motor undersized. Yes, no, it means that it is working pretty good, especially if you are talking about the application with high duty cycle. Yes, because not always it will be possible to size the motor in this way that it will be very hot. But as I said, if the motor is hot, it is normal. It is not some situation that you can look for the failure. Yes, it is normal for servo motors to be hot because they should be hot. Yes, and precisely because of that, there is a warning label on the motor, as you can see here. And I would rather treat it as attention hot and not as you may experience mild discomfort if touched. Yes, so it's important to keep that in mind. I said that if you can check that if you have the application that have high duty cycle, you could check it with the hand if it is warm or not. Let's not touch it, just maybe have the hand very closely or use the thermometer. But if your motor is not hot, then you can think that, yeah, it is oversized a lot. Okay, of course, the servo motors are, let's say, divided. They have the motor part and there is encoder part. Yes, so encoders in the servo, this will be quicker a lot. They are, let's say, divided. We have the absolute encoders and incremental encoders. This is the basic how we can divide the encoders. The difference between absolute and incremental is that absolute, you can read the exact position at every point. Yes, so exact position means absolute position, and in the incremental encoder, you are counting. You are counting the, let's say, increments, the pulses from the zero. Yes, so you have the zero, you have to find, let's say, the zero, and then counting from this zero the increments. And because of that, every time you are shutting down the machine and after powering in on, you will have to do the homing. Yes, the homing to find this zero position. And with the absolute encoders, it will be not always the case. Why not always the case? Because absolute encoders can also be divided in the absolute one single turn and absolute multi-turn encoders. So when you have absolute encoder single turn, you will have the absolute position between one turn of the encoder. Yes, but if you will have more than one turn, so for example, of course, after shutting down the machine, yes, so if there is power failure and you want to read the position from the encoder, if you will, for example, drive the shaft too much, more than one rotation, you will lose the position. Why? Because you can read the position from the one rotation, but if there is more than one rotation, you have to you are losing the position. And because of that, we have the multi-turn encoders. But for multi-turns, you will have to use something else. Yes, and in the market, you can find battery-powered multi-turn encoders. Of course, what does it mean? It means for the multi-turn position, so the position after power off that you can attain, yes, you can read. You need the battery, yes. So encoder needs to be powered in some ways. In this case, you will just use battery to power it. It has some pluses like very good encoder resolution. So it means the number of revolution the encoder can make after a power failure, and you can read it after powering on the machine. But you need to change batteries. Yes, it will depend every 6 months or a year, maybe slightly more or slightly less, depending on the application. Then you have the mechanical multi-turn. So these encoders have the multi-turn part inside, the mechanical multi-turn part inside, and it works as, let's say, the mechanical watch, more or less. So you have the gears inside. After power off the machine and change of the position, the gears will rotate, and after power on, the position will be read to the servo amplifier. This is good because you don't need the battery and don't need to replace the battery. So in case of maintenance, it will be better. But let's say the resolution of that encoder, multi-turn encoder, will be lower, normally about 4 times lower than, let's say, battery ones. And also the dimensions of the encoder will be bigger, so the motor will be bigger because you have to fit somewhere the mechanical parts. Yes. And there is one additional technology, let's say, so multi-turn encoders powered by the phenomena of electromagnetic induction. And this is something that we use in our MRJ5 series. And this combines the good features of both, so the mechanical multi-turn and battery-powered multi-turn encoders, with getting rid of their drawbacks, because you use the electromagnetic induction. What does it mean? When you are rotating, if a small rotates of the motor that is not, let's say, that is not powered, yes, because we have the power failure, for example, the rotation will cause to create a voltage on the windings, because in the encoder you have the windings with the magnet, and this voltage, very, very small little voltage, will power the memory in the encoder, and the position will not be lost, yes, because after power on, it will be read from the encoder. And because of that, they are very compact, and the resolution is very big. Yes, the resolution of the powered by this way, by this technology, encoders are the same as battery-powered one, and you don't need battery. And as I said, we use this kind of encoders in our series, and in this series of motors, we have 26-bit absolute encoders, so single turn, 26-bit, and then the battery-less multi-turn is 16-bit, so about 65,000 revolution after power failure. So it means that there is probably no any case that will lose your position after power failure. So we already know almost everything. Let's sum it up. So what is important when sizing a servo drive? Firstly, as I said, recommended inertia ratio, yes, load to motor. You know already why. Then nominal and maximal torque. Going further, motor speed. So nominal and maximal torque in the application, and motor speed, so the maximal speed of the motor that we will need in the application. And of course the overload, yes. So how much you will be overloading the motor. And combined, we just mean motor operating point. So recommended inertia plus motor ratio plus motor operating point will be, let's say, enough to size the application, to size the motor, but it is hard often to let's say find this motor operating point. And precisely because of that, we will be using Motorizer software to find this. Additional steps before we go to the Motorizer. And Motorizer should be very quick, because I already see that I am a lot. I like to talk a lot, unfortunately. So additional steps. For example, if you want to save the time when commissioning the machine, you can use multi-axis amplifiers, because you can when you are sizing the motor, you will size the exact power of the motor and then find or just choose the which amplifier you will go with. Of course, it will be different by the network, like which network you will use, but also with which kind of amplifier design you can use. So multi-axis amplifier, like the one shown here. So we have from the right 3-axis amplifier and 2-axis amplifier. It can, for example, save the time, yes, when you are doing electrical connection, because for 3-axis that you will have to this amplifier, you will connect even 3 motors. You will just need to make electrical connection to 1 amplifier, so it will be reduce your time like 3 times. The same can be said for DC bus drives. DC bus, like the one shown here, you have the converter and then drive units. These are the drive units. Drive units are also three or two or one axis. So you can connect three or two or one motor to each drive axis. And here, of course, you are connecting the electrical equipment, yes, only to the converter. So the first part of the DC bus system. Later, each of the drive are connected between them. But not only save time. This kind of design can save also the space inside a control cabinet. So as you can see here, when you will use the multi-axis amplifier, this is the example of comparison between one-axis amplifiers, 6 one-axis amplifiers, 400 watts, and two three-axis amplifiers, also 400 watts. So every motor is about 400 watts. So the reduction in the control cabinet is even up to 40%. So the space that you will take is 40% smaller. And with DC bus, it can be even bigger. So here we compared the 1 kilowatt all-in-one system, so normal ones with DC bus, and the reduction of the space, even with this converter, will be about 50%. Yes, and to show you how much it is, in this system you can connect in one system even up to 70 servo axes. 70, so it means that you have, of course, let's say 70 motors. On 1.5 meter, you have the 70 motors, because the length of this servo, DC servo, will be 1.5 meter. So it is a very compact system. And of course, then you have to think about the safety also in the application. If you use the safety or you don't use the safety, it is also nice to know that in our amplifiers we have built in. So let's say when you order the amplifier, when you have the amplifier, you have 10, even up to 10 fail safety functions, and they can be operated via the wire or via the network with CC-Link IATSM, or with EtherCAT network via the FSOE protocol. So let's put it all together and create a methodology for servo sizing, because I told you a little about the additional steps. Then this is the time to create this methodology. So what to look for when sizing a servo drive? Firstly, motor inertia class. Yes, so it will be low inertia, middle inertia, or ultra low inertia motor. Then which type of encoders you will use? Absolute, incremental, power. They need to be multi-turn or not. Yes. Then you have to select the transmission system, or you have to know your transmission system, mechanical transmission system. So if in the application you use the ball screw, rack and pinion solution, two belt, etc., etc. Of course, you will have to calculate the inertia ratio, or just the inertia of your application, of your mechanical load. And then with the, for example, with the software, but also by hand, you will determine the reduced load on the motor shaft. Yes, and we'll use software for that, because then we will reduce the load to the motor shaft, and we'll choose the motor. And additional steps: which type of amplifiers, so which type of supply voltage amplifier, so one phase, three phase, which type of amplifier, so will be all-in-one system or DC bus system, multi-axis amplifiers, yes, and of course the control safety, etc., etc., yes, PLC. Okay, so now I will briefly tell you about Motorizer and how to select something in the Motorizer. I will go with it here. Okay, so this is the Motorizer software. I hope that you can see this this screen. The Motorizer is, as I said, free software that we are using, and you can also use it to size the proper servos from our portfolio. And the design is very easy to understand, because on the left we have some bar with the information. Yes, so for example, which kind of project you want to use, and and also from some steps. I will when we will do one example, I will tell you about that. So which type of system we will, let's say, size? We'll size 3-axis manipulator, 2-axis vertical axis, maybe 3-axis manipulator, but it will be manipulator XZ. So we have two vertical axes working in the tandem, and two horizontal axes working in the tandem, and one vertical axis. Not very complicated application, but it will help you to understand the principle of how to size something in easy way. But also we will use the multi-axis amplifiers to reduce the space, yes, because especially in this kind of solution, you can use just one amplifier, yes, and connect every motor to this one amplifier because of the space reduction, because of the cost reduction. It will be not only less expensive due to the electrical equipment you have to connect, but also less expensive because this kind of amplifiers are cheaper compared to three amplifiers, one axis. Okay, so we will choose new project multi-axis. In this project, when you will go to group 1 and click right button, you will change it as add a power common group and use a multi-axis servo amplifier. Okay, so I will remove the first group, delete. So group 1. Firstly, we will, let's say, size the horizontal axis. The first one I will call X1. And on this axis, we are using the tooth belt. So from step first, you have to choose which exact load mechanism you want to use. And in this case, it will be conveyor. So I'm choosing that. What is the load of the application? So let's say the whole Z-axis with the additional mechanical parts and so on and so on. The mass is 100 kilograms. So we have two axes, yes, two horizontal axes. We'll divide it by 2 because of that. So we have 50 kilograms. Then the belt mass. Sometimes it is good to add this mass if you are talking especially about the chain system. But in case of belt, if the belt is not very, very long, this mass will not make a lot of difference. But let's say I know that this application will have 2 meters. Yes, so the horizontal axis is 2 meters. And because of that, I assume the belt is about 3 kilogram mass. Roll outer diameter. You can also check for these parameters on this graphic. So roll outer diameter is just the diameter of our roll on the tooth belt. In this application, it will be 20 millimeter because this is the mechanical part that's before our designers selected. And then roll inertia moment. As I said, the inertia moment of the load will be calculated, of course, but we also have to calculate the inertia moment of our mechanical system. So if we have this value from, let's say, designers, we'll just write it down, or we can calculate it using this calculator. So basic, yes, for us it is basic figure. The outer diameter of our wheel is 20 millimeters, as I said. The length of that will be 80 millimeters. So we have diameter of 20 and 80 millimeters wheel that our tooth belt has, our module has. This is something that we can check for the documentation, for example, or just measure it. And here the distance to rotation axis always will be 0 because the axis will be in the center of the wheel. Density you can choose, or you can go with the standard one because of that we will let's say calculate the mass, or Motorizer will calculate the mass. And then the last step is to add the quantity of these wheels, in this case 2, because it is the tooth belt module, and reflect. The friction coefficient, the overall machine efficiency, of course, it will be determined by the machine, but in standard cases for the conveyor application or for the tooth belt applications, these values are okay. And the step 2 is to provide, let's say, the gearbox. But firstly, we will go to step 3 because it will be easier to go with the operation pattern to create the operation pattern, and then when we were looking already on the selection of the servo drives, of the servo motors, size the transmission mechanism, so the gearbox, or select it, because we will know the motor speed, for example. So in this application, first thing that we will do is simply travel from 0 to 2000. So I added the trapezoidal characteristic, yes, trapezoidal movement. We will use the feed length time. So I will use the feed length. It is 2000 millimeter that we will travel. Then the time that the travel will take is 1.7 millimeters. And after this travel, we will rest 1 second. And now it is red because it is impossible to create this kind of movement with this acceleration. So we will change the acceleration time for, let's say, 0.05 seconds. So let's say it is quite a big acceleration. Then the next part will be the same, but we'll just return. So we are going to 2000, and now we are returning from 2000 to 0. And this is our duty cycle, let's say. Okay, so I don't see them. Okay, there is no model to do the drive selection. Why is that? I will go with 2000 volts. Yes, this is the solution, because 200 volts, because our multi-axis amplifiers that I choose are working on one phase 200 volts. So I change it in the let's say manual setting, and now we can see that some of them are possible to select already, because if it is, let's say, green, then it means you can select it. The yellow, it means that you can select it, but the parameters are very close to the border of maximum performance of the motor, and red means it is not possible. But 2 kilowatt motors for this kind of application is maybe too big. So let's check if we can do something when we will choose, for example, the gearbox. So we are going to step 2, to the transmission mechanism, and here we can, let's say, set the gearbox parameters. So I will try with the ratio of 3. Why of 3? Because standard, let's say, standard planetary gearboxes on the market that we are using for the servos are divided by the 3, 5, 7, 10, and so on and so on. This is why I started from 3, because I want to use the planetary gearbox, because it will be the precise system. So with ratio of gearbox 3, I can see that now the drives are smaller. Some of them, of course, are red, but some of them are possible, let's say, to use. I will also check if with changing, for example, some of the parameters, I will be able to do something with that, to even smaller it. But probably not. Here we have the bigger power load. Sync. Okay. I would like to size something different, so I will try to go with different voltage, different capacity, and check if some of the motors are possible. Oh, sorry, from this. Which motor is okay? So peak load is too big, for example. Peak load. Okay, because I used a very big acceleration. Yes. So let's say we'll change the acceleration, because we'll just use the movement of the motor will be the same. Yes. But with the acceleration it'll be easier. Okay, then we cannot use this motor because of the maximum speed, and this is sometimes the problem. Yes. So for example, you have to check. You have to find the exact acceleration you want to have at the application, because let's say the smaller the acceleration, the smaller will be the maximum speed, and then you can sometimes use the gearbox to the system. But okay, so let's go back with 0.02 because of the speed, and if we are not able to do anything about that, let's say we will change to 2. And now the maximum speed is okay. Some of the motors, okay, so peak load is too big. So in this system, it will be impossible with this kind of parameters to select proper motors. So unfortunately, if you want to use multi-axis amplifiers, or not just additional module, we would need to change, let's say, the movement, or just go with two-axis amplifiers. So in this case, I will, let's say, delete the gearbox and find if with the motor selection I can select something that is okay. So for example, I will check this motor and then check the gearbox. No, so it's better with one-to-one. Okay, so as you can see, I selected pretty much very let's say very dynamic application. So we are going with motors that the performance of them are very strong. Yes? So the peak load is 4 times. 4 times, it means that the motors have 4 times bigger on the overloading, 4 times bigger torque than nominal one. And still we can go with this system. So we have about not few percent, but a few dozen percent of of what more we can do. But probably sometimes it will be better to go with the bigger motors if we are not sure that in this system, this exact system, let's say, no parameters will be changed. Yes, but I'm pretty sure that in my application, these parameters will be the same for full scope of the working. So this motor, and this is with two-axis amplifier. And now I have to select the same motor, but I will just copy and paste it and change the name, yes, for X2. The same motor, and we have selected our horizontal axis. And from the group selection candidate, we will select, let's say, our amplifier. And here you can, of course, read some data of the motor. So like what is the usage of nominal torque of the motor? And this is about 60% of the nominal torque. Usage of the peak torque of the motor, so about pretty much 400%, so 4 times bigger. And then like what maximum speed, inertia moment ratio, yes. So this is the exact ones that I told you before. Okay, so it is more than 1 hour, and I still have to select one axis. But let's say the selection of this axis will be very the same. I will just add one amplifier, like not common pass, for example, one group, and this axis I will rename for Z. It will be the vertical axis on the ball screw, and without further details, the mass will be 40 kilograms. Mass of the table is the same as, so let's say in this system, I calculated the mass of the load and mass of the table of the ball screw as 1. So this 40 in this place is also the mass of the table calculated. It is good. It is okay to do it that way. It is just to be easier for you to differentiate between these two. Counterweight, of course, we are not using it. And the lid of the ball screw, let's say, it will be 10 millimeter. Ball screw inertia moment, the same as before. We can calculate it if we are not knowing yet that. So outer diameter 16, length 440, distance 0, density the same, and only one quantity because we have only one ball screw in the system. Now the overall machine efficiency, friction coefficient, and thrust load will be like here because it is standard and we are not generating any thrust load of this ball screw. We have to just change in the option the angle to 90 degree. And with the operational pattern, our duty cycle will be like that. So first we will wait for the horizontal axis to move to the position, and it would be 2.7 seconds, I think. And then we'll go to the position of 300 millimeter in the time of 0.4, let's say, additional rest time that we'll need to put the detail back. change the time for the acceleration, the same as before. Okay, and we have our axis. And once more, I will copy the parameters because it will be like that. So this is the full duty cycle. Okay, and now we have to select some motor. At this point, I don't have the problem. I will just select the motor with which one it is the best for me. Let's look. So we'll go with the first one. So 500 watts motor. And here, of course, without any gearbox because the motor is very small. The speed is very big, it's about 80%, and we just don't need the gearbox, especially that with the ball screw, it is better to don't use the gearbox because when even changing the lead of the ball screw, for example, for 16, will change the parameter of the application. Yes, so I can change for the 5 and change the, let's say, ratio. Okay, so I think this is all from the Motorizer because we are a lot after time that I should present. So going back to the presentation and then to your questions. Before of course going back to this question, I have one thing also for you. So the question, or just to tell you that we plan to have more than one this kind of English webinars, English these workshops. And the next one is using predictive maintenance in drives. This is very interesting. This is very interesting topic of how the predictive maintenance functions that are built in our servo drives can help you with maintenance of your company.